Black holes are one of the most fascinating objects in the universe. They are regions in space where the gravitational pull is so strong that nothing can escape from them, not even light. The concept of a black hole was first introduced in 1783 by John Michell, a British scientist. That the existence of black holes was confirmed through observations and mathematical modeling. What is a black hole, and how was its existence confirmed? A black hole is a region in space where the gravitational pull is so strong that nothing can escape from it, not even light. This happens when a massive star runs out of fuel and collapses in on itself, causing a singularity, a point of infinite density and gravitational attraction, to form at the center of the black hole. The existence of black holes was confirmed through observations of the effects of their gravity on nearby stars and gas, as well as through mathematical modeling of the behavior of matter near a black hole. When an object falls into a black hole, it is stretched and compressed by the tidal forces near the singularity. These forces are so strong that the object is torn apart and its matter becomes part of the singularity. The point of no return for anything that crosses into a black hole is called the event horizon, beyond which even light cannot escape. Anything that crosses the event horizon is believed to be trapped inside the black hole forever. When an object gets close enough to a black hole, the gravitational pull becomes so strong that it can no longer escape. This is because black holes have an incredibly strong gravitational force, which is caused by the immense mass and density of the singularity at their center. The closer an object gets to it, the stronger the gravitational force becomes, until eventually, the object crosses the event horizon and falls into the black hole. Black holes can have a profound impact on the surrounding universe. As matter falls into a black hole, it can form an accretion disk around the black hole, where the matter spirals inward and heats up, releasing intense radiation. These accretion disks can be observed by telescopes, providing valuable insights into the properties of black holes. Black holes can also create powerful jets of energy and matter that extend for thousands of light years, shaping the formation of stars and galaxies. Actually, the creation of black hole deals with the destruction of star. For this, let's see how stars are made. Stars are formed from the gravitational collapse of clouds of gas and dust, and they can have a mass of 20 or more times that of our Sun. A disturbance, such as a shock wave from a nearby supernova or the collision of two clouds of gas and dust, can cause the nebula to begin to collapse under its own weight due to gravity. As the cloud collapses, it becomes denser and hotter, causing it to spin faster and flatten into a disk shape. This protostar is not yet a true star, but it is a hot, dense ball of gas that is slowly accumulating more mass from the surrounding material in the disk. When the temperature at the core of the protostar reaches about 15 million degrees Celsius, nuclear fusion reactions begin to occur. These reactions fuse hydrogen atoms together to form helium, releasing energy in the process. This energy creates an outward pressure that counteracts the force of gravity, keeping the protostar stable. Depending on the mass of the star, it may go through several stages of fusion before eventually running out of fuel and either collapsing into a white dwarf, neutron star, or black hole, or exploding in a supernova. Why star runs out of fuel? Eventually the hydrogen in the core is used up, and the fusion reaction slows down. This causes the pressure in the core to decrease, allowing gravity to compress the core further. As the core becomes more compressed, it becomes hotter and denser, eventually becoming hot enough to start fusing helium into heavier elements like carbon and oxygen. This process produces more energy, which causes the outer layers of the star to expand and cool, forming a red giant. Eventually, the star will run out of helium fuel as well, and will either collapse into a white dwarf or undergo a supernova explosion, depending on its mass. This explosion is so powerful that it can outshine an entire galaxy for a short period of time. If the remaining mass of the star after the supernova is large enough, the core will continue to collapse under the force of gravity until it becomes a singularity. The gravitational pull of the singularity is so strong that it creates a region of space around it where the gravitational pull is so strong that nothing, not even light, can escape. They are called black holes because they are objects in space with such strong gravity that they appear completely black to an outside observer, since no light or other radiation can escape from them. The name was first used by physicist John Wheeler in the mid-20th century. The first image of a black hole was captured in April 2017 by using a technique called the Event Horizon Telescope, EHT, which is a network of radio telescopes located around the world. The target of the EHT's observation was a supermassive black hole at the center of the galaxy M87, which is located about 55 million light-years away from Earth. The black hole has a mass of about 6.5 billion times that of the Sun and is surrounded by a hot, glowing disk of gas and dust. Black holes can merge through a process called binary black hole merger. This occurs when two black holes are in close proximity to each other and begin to orbit around each other due to their gravitational attraction. Over time, their orbits will decay due to the emission of gravitational waves, which are ripples in spacetime that are produced when massive objects accelerate. As the two black holes continue to orbit each other, they will eventually merge into a single, more massive black hole. During the final moments of the merger, the gravitational waves emitted by the system will become extremely strong and cause the black holes to spiral in towards each other at a faster and faster rate. This process is known as the ring-down phase, and it lasts only a fraction of a second. If an object, such as a star or a planet, comes too close to a black hole, it will be torn apart by the strong gravitational forces of the black hole in a process known as spaghettification. This is because the gravitational forces on the object are much stronger on the side closest to the black hole, and much weaker on the side furthest away, causing the object to be stretched into a long, thin shape like spaghetti. As the object falls towards the black hole, it will first cross the event horizon, which is the point of no return where the gravitational pull of the black hole is so strong that nothing can escape from it. Once inside the event horizon, the object will continue to fall towards the black hole's singularity, where it will be crushed to an infinitely small point of infinite density. If a black hole were to come closer to an object, such as a star or a planet, the gravitational forces between the two objects would become stronger, causing the object to experience tidal forces that could rip it apart. The effects of the tidal forces would depend on the mass and size of the black hole, as well as the distance between the object and the black hole. Is it possible to escape black hole? The only way for an object to escape a black hole would be to travel faster than the speed of light, which is currently believed to be impossible according to the laws of physics. Even if an object were able to approach the speed of light, it would require an infinite amount of energy to escape the gravitational pull of the black hole. It is worth noting that there is a concept known as the gravitational slingshot, where an object can use the gravitational pull of a massive object, such as a planet or a star, to increase its velocity and escape its gravitational field. However, this would not be possible with a black hole, as the gravitational pull is too strong and the escape velocity is greater than the speed of light. Black holes are one of the most important predictions of Einstein's theory of general relativity, which describes the behavior of gravity in terms of the curvature of space and time. According to general relativity, massive objects warp the fabric of space and time around them, causing other objects to move in curved paths. In the case of a black hole, the curvature of space and time becomes so extreme that it forms a region of space called the event horizon, beyond which no matter or radiation can escape. The point of no return, beyond which even light cannot escape, is known as the Schwarzschild radius. This phenomenon is a direct consequence of the extreme curvature of space and time near a black hole. Furthermore, general relativity predicts that the strong gravitational fields of black holes cause time to slow down, a phenomenon known as time dilation. It is currently not possible to use a black hole as a means of traveling to another galaxy through a wormhole. While black holes can distort space and time, the extreme gravitational forces they produce make them incredibly dangerous to approach. Objects that get too close to a black hole's event horizon, which is the point of no return, are pulled in by the immense gravity and crushed into a singularity. In addition, Even if it were possible to somehow navigate around a black hole, the distances between galaxies are so vast that it would take hundreds of thousands or even millions of years to travel from one galaxy to another, even at the speed of light. While black holes are fascinating objects that have captured the imagination of scientists and the public alike, they are not currently considered to be a practical means of intergalactic travel. One of the most intriguing possibilities that has been explored is whether it is possible to create miniature black holes by using Large Hadron Collider, a powerful particle accelerator. According to Einstein's theory of relativity, mass and energy are interchangeable, and the energy of a particle determines its mass. As particles are accelerated to higher energies, their mass increases accordingly. Einstein's theory also predicts the mass curves space and time, generating the phenomenon of gravity. As particles travel at high speeds within the LHC, they can warp the fabric of space and time around them, effectively creating gravitational fields. When two particles collide within the LHC, they can focus the energy of each other, much like two lenses can focus light. If the energy of the collision is high enough, it is theoretically possible for a miniature black hole to be created.